Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about trees. A tree is a connected, undirected graph having no simple circuits. And so in particular, no simple circuits. Let's give some examples. One example might be something like this. You can see this is a connected, so you don't have something disconnected over here from this piece, undirected graph, but it doesn't have any simple circuits. Let me give you one that has a simple circuit. The cyclic graph of order 4 here, it definitely has a simple circuit. So this is not a tree, where this one is. Some graphs may look like they have a simple circuit, but maybe they don't. Let me give you an example. A, B, C, D, E, F. So we're going to have C be pendant off of A here. This is going to connect down to F. F will connect to E. E will connect to B up here. And D is also pendant off of F here. So this is a tree. Note that we can move this point B over here, in which case we won't have that crossing, and then perhaps it's clearer that this is a tree. However, if I have A, B, C, D, E, F, let's connect the points from here to here and then down to here. Let's connect here to here and then up to here, but let's go back over to here and down this way here. You can see we have a simple circuit, and therefore this is not a tree. Let me give you another example of something that's not a tree. Again, A, B, C, D, E, and F. We're going to connect things up from here to here, from here to here, and from here to here, and also from here to here. Notice that if we move this point B over here, you can see that this is not connected, and that implies then it is not a tree. We have a theorem. An undirected graph is a tree if and only if there is a unique simple path between any two vertices of the graph. So let's give an example here. This is clearly a tree. We have A, B, C, and D. We can go from A to C on a simple path from A to B and then B to C. We can go from B to D, B to A to D, and there's only one way to do that. Between C and D, between A and any of the others, we just follow the straight line path. So this, you can see, will be a tree, because between any two vertices in this graph, there is a unique simple path between those vertices. So how do we prove this? Well, suppose you have a tree. If you have a tree, if you take any two vertices, then because you have a tree, it's connected. That implies there is a path. From U to V. If there were two, then you could form a circuit. What we need to do now is prove in the other direction. So in the other direction, we assume that between any two vertices there is a unique path, a simple path between them. We need to prove then that what we have here is a tree. So assuming that there is a unique simple path between any two vertices in the graph, that implies connected. Also, if there were a circuit, then we could form two paths by dissecting that circuit. Between two vertices. Therefore, we have a tree. And that's the end of the proof. A rooted tree is a tree with one vertex selected as the root and every edge is directed away from the root. So you have some root. You may have other vertices, but all of the other edges end up moving away, farther away in terms of the distance from counting the number of vertices from the root. There's your root right there. More specifically, on our rooted trees, we're going to have directed edges, and all of these edges will be directed away from the root. So, let's suppose we have this kind of setup. A coming down to B and C, D, E, F, G, and H. We say that the initial point on one of these directed edges is the parent of the child. So this is also a child of this parent. These two, both being children of the same parent, are siblings. So these are going to be siblings of this parent. These three will be siblings of this parent. If we focus our attention at this particular vertex, it has a bunch of different ancestors. So if this is the focus here, then these are the ancestors. We assume, of course, that the root does not have an ancestor, so we only apply the term ancestors to vertices that are not roots. Well, if you can have ancestors, then you can have descendants. All of these other points in the graph are descendants of the root. The descendants of vertex B will be D and E. They're descendants. So if we're focusing right here, then these two are the descendants. If a vertex has no children, then we call that a leaf of the tree. So we'll have 5 leaves in this particular case. Any vertex that has children is called an internal vertex. So we'll even say that the root is also an internal vertex unless you're dealing with a tree which only has a root with no edges, in which case we'll not say that this is an internal vertex. It's a leaf. We can form subtrees. If this is B with D and E, so this is a subtree. So this is our definition. A subtree of a vertex has that vertex as root and all descendants of that vertex. So you can see that if I included A without the piece on the right, that would not be a subtree because it has to include A and all descendants. But I can choose C along with F, G, and H, and this would also be a subtree. An in-airy tree is a tree where every internal vertex has n children. So you can have a binary tree we can call it a two-airy tree as well. Every vertex that's internal has 2 children. We could have a ternary tree. Every internal vertex has 3 children for a 3-airy tree or a ternary tree. I guess the 4-airy tree or quaternary tree will have 4 children for every internal vertex. By the way, these don't have to keep going on like this. We could have something like this, where this last vertex over here has no children, and it's still a 3-airy tree. You can tell that these trees are a lot like what you would draw for, say, family trees. An ordered rooted tree is a tree where the children of each internal vertex is, these are ordered. Just like in a family tree. Might start off here and have, if this is A, B, and C, this will be the first, this will be the second, and then let's suppose we have a first, second, and third, a first and a second over here. And so the children of these internal vertices will be ordered in some way, usually by assigning maybe a numeral order to them, first, second, third. We'll also usually draw them in this order. First will be the lefternmost, and then followed by the second, and then the third, and so on. You can form subtrees. There's a left subtree off of this point A. Well, it'll be rooted at B and have all of its children. There's a right, then, subtree just involving C together with its children, 1 and 2. There are some basic theorems about trees. A tree with n vertices has one less than that edges. Let's look at an example. Here's a tree, and we have 1, 2, 3, 4 edges. 1, 2, 3, 4, 5 vertices. So if n is equal to 5, then n minus 1 will be 4. The proof is by math induction. And I'll let you look that up in your text. Another theorem just based upon counting. A full M-ary tree with I internal vertices has n equals m times I plus 1 vertices. So I guess this would not be full. But if I have this, now it's a full binary tree or two-ary tree. And let's see how this works out. In this case, how many internal vertices do you have? This is a two-ary, so m is 2. Internals, you have 1, 2, 3. If you take 2 times 3 plus 1, you'll get 7 vertices. Is that true? You have 1, 2, 3, 4, 5, 6, 7. And so this one's not full, but if you have a full two-ary tree like this, you're going to have m, the number coming out on each level, times the number of internal vertices, and then plus 1 as the number of vertices altogether. With the two-ary tree, you can separate this into levels. The number of internal vertices, 3, since you're dividing off from the first one by 2, this is the extra 1 that you're going to add. We're going to have 2 to the 1, 2 to the 2, which is 4, 2 to the 0, which is 1, 4 plus 2 plus 1. That's the way to add these up. If you were with an M-ary tree, it would be 3 to powers that you would be adding up. 3 to the 0, 3 to the 1, 3 to the 2. What would this be? 9 plus 3 is 12 plus 1 is 13. 13 vertices in a three-ary tree with these two layers of internal vertices. You can see that here. Where here you have 3 squared or 9 vertices, 3 to the 1, or 3 vertices and 3 to the 0 with that one remaining vertex here. That gives you the 13 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the way to count this, if you have an M-ary tree with I internal vertices, multiply and add by 1, increment by 1 to get the total number of vertices. A more complete theorem says that a full M-ary tree with, first part, I internal vertices has n equals m times I plus 1 vertices and L equals m minus 1 times I plus 1 leaves. So in a binary tree with 1, 2, 3 internal vertices, how many leaves do you get? It's a 2-ary tree here, 2 minus 1 times I, the number of internal vertices, plus 1, gives you 1 times 3, which is 3 plus 1 is 4. 1, 2, 3, 4 leaves. If, on the other hand, you have a full M-ary tree with n vertices, then how many internal vertices do you have, and how many leaves do you have? Well, the number of internal vertices will be n minus 1 divided by m. And you can just get that from solving this equation here by moving the 1 over to get n minus 1, and then dividing by m to get the number of internal vertices. How many leaves do you have? Well, I is going to be replaced by n minus 1 divided by m. So you're going to have a fraction. You'll convert this to m over m. And then when you FOIL that out, you're going to get m minus 1 times n plus that extra 1 there. To better see where this formula came from, we start with m minus 1I, but I gets replaced by n minus 1 divided by m plus 1. This first term is going to be a fraction, and you add fractions by having a common denominator. So you're going to have m down here on the top. We're going to have to distribute. When we do distribute, we'll get m minus 1 times n, but then we'll get minus m minus 1 plus m, which is left over here. So when you distribute the minus here, you'll get a negative m and a plus m. These will cancel. Negative, negative gives you plus. That's how you get plus 1 right here. There is a third part to this. Here we've given the number of internal vertices. Here we've given the total number of vertices. But what if we give you the total number of leaves? Then we need to determine the number of vertices and the number of internal vertices from that. L times m minus 1 over m minus 1 vertices. And how many internal vertices? It's going to be L minus 1 over m minus 1. This first formula comes from solving for n over here. You'll move the m over so you get L times m equals m minus 1 times n plus 1. You need to subtract the 1 over. When solving for something, n, you always take the reverse of the order of operations agreement, and since multiplication takes precedence over addition, you'll deal with this addition first. And you use opposite operations, so if it's added, you'll subtract. L times m minus 1 is m minus 1 times n, and then you'll divide the m minus 1 over, obtaining this formula here. On the other hand, for this formula, we already have the formula where the number of leaves is m minus 1 times I plus 1. All you have to do is subtract the 1 over and then divide the m minus 1 off to obtain this formula here. We've already shown that properties 2 and 3 follow from property 1, so all we really have to do is prove property 1. But we've already proved the first part of property 1, that n is m times I plus 1. So that part is done. The only thing left to prove is how we can count the number of leaves. Well, the number of leaves is the total number of vertices minus the number of internal vertices. And we already know that the number of vertices is m times I plus 1. We're just subtracting I. So if we take these two terms and factor the I out, we'll end up with m minus 1 times I plus 1. And the proof is over. The level of a vertex in a rooted tree is the length in terms of number of edges in the unique path from the root to that vertex. So, for example, the root itself is on level 0. These two are on level 1. We have one edge connecting those to the root. Each of these is on level 2 because the unique path will involve two edges. The height of a rooted tree is the maximum level of its vertices. So in our basic tree over here, we have two vertices that are level 2 and nothing higher, so this is a height of 2. A rooted M-area tree is balanced if every leaf is of height h or h minus 1. We're going to allow that level of deviation in order to be balanced. But if we have something like this, this one is not of height 2 or 3. The height of the tree is 3 here, 1, 2, 3 edges back. But here you have a leaf, and it's of height 1. So it turns out this is not balanced like this. If we add one more generation here, then it would be balanced. In an M-area tree, of height h, there are at most m to the power of h leaves. We're not assuming it's necessarily full, but if it is full, that'll give you the highest number you could possibly get. In this case, the height is 2, and it's a 2-area tree. So you'd expect 2 to the 2, or 4 leaves. 1, 2, 3, 4. Let's do a 3-area. And here its height is 2, so 3 to the 2 is 9. We expect there to be 9 leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9. If some of these little branches don't go all the way to the height of 2, then you could have less than 9. But if it's full, that gives you the highest number of leaves that you can get, and then it will be the m, the number of branches coming down from each internal vertex, to the power of the height h. The proof is, of course, by induction. When you have a statement like this, it's really an infinite number of statements for each m and for each h. For a given m, you have to prove this for each h, each height, 0, 1, 2, 3, and so on. In which case you actually have an infinite number of statements to prove. You always do that with math induction, unless you can find a constructive way to make the proof. As a corollary to our last theorem, if an m-ary tree has height h and L leaves, then h is greater than or equal to the ceiling function of the log base m of the number of leaves L. How's that for an interesting estimate? If full and balanced, then the height will in fact equal the ceiling function log base m of the number of leaves L. So how are we going to prove such a thing? By the last theorem, the number of leaves is less than or equal to m to the power h. So if we're trying to solve for h, we need to take the log base m of both sides. If m is bigger than 1, then that log will be monotone increasing, so it'll preserve the direction of the inequality. And when you take log base m of m to the h, you get, of course, h. So we get h is at least log base m of the number of leaves L. But keep in mind, the log base m of L may not be a whole number, which means you have to look for something that it will be a whole number, perhaps larger than this. And so if h is a whole number, it will be at least as big as the ceiling function of log base m of the number of leaves L. We have only to prove that you get equality if the tree is full and balanced. Then L will be at least as big as m to the power of h minus 1. That implies then that log base m of L is bigger than or equal to h minus 1. We already have this as less than or equal to h, and I've got this inequality. This needs to be a strict inequality because this is a strict inequality. So log base m of L is in between h minus 1 and h. So the worst you can do is look for the ceiling function, because h has to in fact be a whole number and not some weird irrational number or even a fraction in between. And so you can take this ceiling function and make this into an integer, and that will give you equality. It has been my distinct pleasure teaching you this course in discrete mathematics. Unfortunately, most of the interesting aspects of discrete math occur in the sections of your text that we didn't have time to cover. I think you'll agree that we were moving flat out this whole term, and we covered all that we had time for. However, I would encourage you to look at some of the sections that we didn't cover in the text, because a lot of the really interesting, compelling theory occurs and examples occur in those sections. Thank you.